Well, yeah. We just got some direct products.
I read this whole long
It's
to find out one thing. It was like half a paragraph.
All right, good morning, everybody. So we'll go ahead and get started. So I posted the final assignment on Monday to Canvas. All right, so be sure that you check there for that. Today, I'd like to continue talking a little bit more about rings and focusing on a couple of things that are related to questions on the homework assignment, okay, just to make sure that everything is clear there with what I'm asking for. Okay, so. All right, so today we'll focus on working through a few examples just to play around with rings a little bit further. And so last time we wrote down the definition of a ring. Okay, so remember that it was just this. Okay, so we are now in the setting with two binary operations, one referred to as addition and one as multiplication. Okay, so we have a set together with these two operations. Under addition, we have an abelian group, all right, so the sort of thing we've been talking about much of the semester. And we have the second operation of multiplication. And like we've been talking about with groups, there's an associativity property there. And then as far as how addition and multiplication get along, we have the distributive properties here. Okay? But in general, remember, under multiplication, a ring is not a group. Even if we throw away 0, in general, we don't have a group. Okay, so the group is only under the operation of addition, whatever that would happen to be in a particular context. And so last time, at the end of class, we wrote down, I think, a couple of examples of rings that, again, are already familiar. So the integers mod n. Another familiar example of a ring comes from linear algebra. And so there is a question on the homework assignment related to this. All right, so matrix rings. And so here, just to keep things nice and small for writing, we'll stick with the 2 by 2 case, but everything that we're going to say here is true for any size of matrix. All right, so for example, here we'll think about, as we have typically been doing, matrices that have real number entries. Okay, so this notation here stands for the set of 2 by 2 matrices. Now, altogether, we don't have any invertibility condition that we're specifying here. It's just the set of all 2 by 2 matrices with real number entries. And the operations here are the familiar ones that you may remember from linear algebra. So when we add matrices, it's simply entry-wise, all right? So entry by entry. So here, we take two of these 2 by 2 matrices and add them together. Then the addition, again, is just defined by summing entry-wise. Okay, so the sum here would be given by this, and then the multiplication is just the usual, so I won't write out the rule for that. We've been using that throughout the semester, so the multiplication here is just the usual. Okay. So one can check. It's not awful to do. It's a little bit tedious, but one can check just by using definitions of these operations that the ring properties here are satisfied. So as far as forming an abelian group under addition, here the identity would be what in this case? So what we were writing up there in general or generically just as 0.
The zero matrix?
Zero matrix, exactly, right. So all we're doing here again is just entry by entry addition of real numbers, right? So underlying this is really just real number addition. So the zero here would be this, and then the fact that we have an abelian group so that addition is associative, that we have inverses and so on is just coming from thinking about real number addition entry by entry. Okay, so I'll leave it at that. As far as the multiplication is concerned, so one can again crank through this and check it directly. It's a little bit tedious to do, but one can check that the multiplication is associative if one does it directly. We also talked about this thinking about matrices as representing functions, right? And using the fact that function composition is associative. So that's a little bit faster way to verify the associativity here. Similarly with the distributivity, one can check it directly or also think about matrices as representing functions and then work through it that way. Okay, so again, I don't want to spend a lot of time working through that here, but I'll just say that these properties hold for these operations on matrices. The unity here, so remember unity is the identity for the multiplication operation, if there is one. So as we know, for matrix multiplication, that's just the identity matrix, right? So here, the unity would be this 2 by 2 matrix. And what would the units be in this ring?
The units would be all the matrices with a determinant that's non-zero, with a non-zero determinant.
Okay, so with a non-zero determinant, right? So here, if the operation, multiplication operation is just the usual matrix multiplication, then the inverse is going to be the usual inverse, right, with respect to matrix multiplication. And we know that there is such an inverse precisely when the matrix determinant is not equal to 0. Okay. And so we have notation for that collection of things, right? So here, the invertible 2 by 2 matrices, that is the group that we refer to as a general linear group. Right? So 2 by 2 matrices with real entries. Okay, so those would be the units here. And unlike the examples that we were talking about last time, the integers and the integers mod n, so those are commutative rings. Remember when we use the term commutative ring, that has to do with the multiplication operation. So is multiplication commutative or not? We know that matrix multiplication is not a commutative operation, right, in general. There are pairs of matrices that commute, but in general, AB is not equal to BA. Right? So this is a non-commutative ring. Okay, so here then, with the homework, I'm asking you to think about something similar, but now matrices whose entries are not real numbers, but rather matrices now where the entries are integers mod 2. All right, so here, 2 by 2 matrices. Where entries are mod 2, and so I'll say that generally speaking, in terms of our operations, what we've talked about here except now there are only 2 possible values for each entry, right? So everything has to be a 0 or a 1. And now everything that you're doing is mod 2, right? So in the matrix entries here, any arithmetic that's happening is not the real number addition multiplication, but it's mod 2 addition and multiplication. Okay. And I had you in a previous homework do something similar to this, I think with special linear group with integer mod 2 entries. So this will be similar to that. Okay. And so in general, So just in terms of thinking about units, for a 2x2 matrix, we have a formula for the inverse matrix, right? So it is 1 over the determinant, so 1 over AD minus BC, and then the entries look like this. Okay, so that's a generic way of writing down an inverse of a 2x2 matrix, of course, so long as this quantity down here is not equal to 0, so as long as the determinant's non-zero. And so part of what you're thinking about in this exercise is now, if we move to the setting where all of the arithmetic, the addition and multiplication is mod 2, then what does this turn into there? Okay, so what's the invertibility condition, and then what form does the inverse matrix take in that particular context, right? And so, for example, there are only these two elements in the integers mod 2, right? So each thing is its opposite, for example, right? Mod 2, -1, and 1 are the same thing. Okay, so you'll need to think about this thing, but in the context of mod 2 arithmetic. So then I'm just asking you to work out or think about similar sorts of things to what we talked about here, but in this case. And so in this case, for example, you can write down all of the matrices. Right? There are infinitely many matrices there with the real number entries, but here there's a finite number, and you can write those down. All right, so there's a third example of a ring. All right, and then before we get to the fourth one, so the other one that I want to focus on, so just by way of working our way toward that. So there's a problem toward the end of at the end of the section. So I'm going to write it down here, and I'm going to pause for a moment. I want you to think about this or just chat about it with someone, people around you. All right, so here the question is asking for an integer n. Showing that this ring, so the integers mod n, so operations addition and multiplication mod n, need not satisfy following properties. All right, so 1 here, a squared is equal to a, implies that a is equal to 0 or 1. AB equal to 0 implies that a is 0 or b is 0. And then the last one here, the products AB and AC are equal. And this number a is non-zero. Then b has to be equal to c, right? So, and this here is a cancellation property, right? If I have two products that are equal, there's a common factor. Can I cancel in general? And so here this is saying that in general, unlike in groups, right? So in groups we have the one operation, and we can cancel there. In a ring, under addition, because we have a group under addition, we can cancel, but under multiplication in general, we cannot. All right, so I'll pause there. I'd like you to take a couple of minutes and think about these, see what you come up with here to show that in general, these three things need not hold. And again, we're just talking about multiplication here, mod n, right? So that's our operation. Chat about people close to you, around you, however you want to do it, see what we come up with.
Because we're at its then it's a group of multiplication, which means left cancellation would work. so that can't be right. That's all I figured out. We always need over 2. No.
For C, I'm just on something, I'm just.
So you want
A is like standard.
So,
oh, what if it's 3 and B is 3 and we're
A squared, you know.
I did.
then A and B would
Give a different
well,
one.
which is 0.
I just.
So that brings that.
I knew it couldn't.
3, and if A is 3, then oh, okay. So,
Yeah, there's 3 squared is 9, which is 3 more.
I found one that,
So it's the last, 3 squared equals 3, is D6.
and that's
And
the integers function. Like that's 131. So for the second one,
What's the important?
let's say so A and then
yeah, this is counted.
then 3 times 3 is just A equals 0. Yeah,
Basically the A squared.
but neither A nor B is 0.
Yeah, that's right.
Yeah, because.
With the third one, let's say that you have,
That's good. Oh, you can say the thing. So let's say.
so A's got to be 3, and
Yeah, like 5 we can.
5 and
5
8,
squared.
maybe.
Okay.
Yeah. Oh yeah, I haven't gotten to one yet. Oh, it doesn't work.
Yeah,
that way?
this one.
Yeah, as soon as
The factors.
So 3 squared is 9.
Well, think about it like this.
9 is 0, like 0 is not equal to 2.
Oh, okay, but what if A is 4? Wait, no.
Oh,
It's
it's
squared
A
is
is 4.
Oh, there are no elements in order
Even
to.
though we divided
And,
by numbers
No,
so any, if n is any even.
No, that's not true. Yes, it is. This was on the midterm, and then. Okay, so there are 9, wait, no, but it's not Greek. It's not Greek, so you have to read this.
And divided by 2 is extra time.
One squared plus 9.
So you have 2 then divided by 2. So how many times is that going to? 9.
Oh, so this is 7,
4.
How many times
and
is
all
it
this
squared?
could be its own.
You mean like in what context, like mod it? or-
Yeah.
Oh, you're right, it doesn't work for that, yeah.
It does not follow. So I think it's
Well, n squared goes to n, right? We're thinking about like arbitrary.
No, it doesn't because it's 11 by 4. We know that.
Right, oh, you just.
Right, you know that n divided by 2 is 2 by 4 because n divided by 2 is equal to 3.
So we go down to
So
8.
it has to be.
See it.
Yeah, that's what I'm doing.
Oh, okay.
So that's
Yeah,
the
factors.
factor.
Properties 2 and 3 still work.
Does that make sense? Does that jump make sense
So
there?
n is an even number.
Because you have 4
Right.
and B is 2.
You're trying to say.
You know it's not.
And you can use 4.
That would mean that n divided by 2 is even.
Because if you were to divide this by
And you
4,
can use
that's
2,
n
say,
for me was like 2 times n over 2.
and go with 4 and so on.
Right.
What about you?
But since you know that every 2 times n,
For property
every 2
they
n minus
equal
2
to
goes into the next
equal to
one.
4
Right,
and
number like that.
How many,
to 6.
Like for example, you have
Are you
10.
supposed to?
Five times
Oh, okay. Yeah, and then, wait, no.
2 10
Sorry.
and then 1 left over. So,
Because I'm sure what you're thinking makes sense, I'm just not saying all the steps that you're going
so
to
let's,
get to.
so let's choose 98, right? 98 divided by 2 is 40.
49.
So you 49 squared. Oh, so it's 49, 49. That cancels, so it's 47, 45, 43, and you know what's left with 1.
Wait a minute, D12, everything's
Really short as opposed to level 49.
Well, no, I mean, like, you take away 98, you have 47, and it's 45, and 49. Does that make sense?
Right, so 49.
So you end up with 1 equals 49.
Yeah, there's a few different.
Does that make sense? That has to be
You're looking
the.
at 49 squared.
Wait,
More than times 49, right? And so, go back
sorry,
to
I was thinking
you
A
take away 2
What happens
times. Right, so,
49 times.
so it gives you
Take away 2 of them.
so it's 47 times 49, and 45 times 49. Wow, and you know that this is not.
Thank you so much.
That's not what those small numbers are. Yeah, I think you were right, I'm still for one of them.
Yeah, but I got the first one wrong.
It's weird, like, I don't know, like, it doesn't matter, I just
Yeah,
thought it.
the first one saying for all unknowns, it's
Well, that does matter, that's like a general condition, I think. So,
right?
if you have, no,
Wait, where are you getting that from?
So, it has to be a given number, that's not the
Same. You can
so it has to be one number, and
No, I didn't try to.
divide by 2, it's odd. So the prime recognition has to be 2,
I was gonna say
not
front.
an odd number.
Yes.
Are you front loading this?
Don't get enough. Oh, yeah, this
I like
one's.
the first, so.
All right, so let's see what we have here. What about for the first one, number 1? Anyone have an example there?
A is 3 and N is 6.
A is 3 and N is 6. Okay, so if we take N to be 6, A to be 3. Okay, so then we get 3 squared or 9. But 9 mod 6 is equal to 3, right? And in the integers mod 6, 3 is distinct from 0 and 1. Okay, so that works there. What about second one?
We can make N 6 again.
Okay.
And then A and B are 3 and 2.
Okay. All right, so the point here with B, or with 2 rather, is that 6 is composite, right? So it factors in this non-trivial way. So we have these non-trivial factors here, 3 and 2, and so we can multiply those together to get 6, which is 0 mod 6, okay? Then the last one.
So, N equals 6, A could be 3, B equals 2, and C equals 4.
Three, 2, and then you said
4.
C is equal to 4. Okay, right, so there. Right, so 3 times 2 is 6, 3 times 4 is 12, mod 6, that's 0, right, just as 6 is. Okay, so here, 0, here mod 6, these are all 0, 2 is not equal to 4. All right, so in general, we cannot cancel. Okay. All right. All right, so those are a few small examples of things that can be different in multiplication in a ring than you're used to thinking of multiplication behaving, either in a group, okay, in particular here with the cancellation, or just when you think about multiplication in the usual contexts, right? So in the integers or the rational numbers or something such as those. So one thing that I want to point out with these examples here is that in the end, here, all of these statements here, so 1 through 3, really boil down to the middle statement, right? So this idea here of being able to take two non-zero things and multiply them together and get 0. All right, so for example, in 1, saying that a squared is equal to a is the same as saying that a squared minus a is equal to 0. And if we factor here, this would give us the product a times a minus 1 is equal to 0. Right? So again, as far as arithmetic in rings is concerned, I pointed this out last time, but basically the takeaway from this was that you can do the things that you would expect you'd be able to do, right? So in terms of factoring and distributing and so forth, all of that works as expected. Similarly with 3, if we say that AB is equal to AC, that's the same as saying that the difference of AB and AC is equal to 0, which is the same as saying that A times the difference B minus C is equal to 0. Okay. All right, so these all in the end really come down to the second property here, and being able to multiply together two non-zero things and get 0. All right, so thinking about settings then where we can count on the usual behavior. So for example, being able to cancel under multiplication, take non-zero things and multiply them together and end up with something non-zero. Where we have the properties say that working with integers or real numbers you'd expect, what are the solutions of this equation here? Just 0 and 1. All right, so the additive and the multiplicative identities. So if, for example, in 2, if we suppose that A is a unit, okay, and then we also suppose that A times B is equal to 0, then that forces B to be equal to 0, right? So in other words, in that case, we can't have a product of two non-zero things giving 0. Okay. Why is that? Well, basically, if we have a unit, then we can cancel here, right? What does cancellation amount to doing? In general, if I wanted to cancel here, if I'm talking about a unit, if I'm supposing that A is a unit, then I can multiply both sides by A inverse, right? And I can cancel it. So here, just to write it all in one line, B is equal to 1 times B, right? I'm using the unity here, the multiplicative identity. But then 1, oops, I want to put the inverse on the left here, is the product of A inverse with A, right? And then here, multiplication is associative, so I'm doing this in a more pedantic way here, but remember the point of associativity is that we don't have to write the parentheses in general, right, when we're writing, manipulating expressions like this. Okay? So if I move the parentheses over, then here, if we're supposing that A times B is equal to 0, okay, then we end up with A inverse times 0, and that gives us 0, right? So remember, so here, so 0 times anything is equal to 0. Okay. So if we have then a factor that is a unit, then we can cancel. All right? So For example, in the integers mod p, right? So here I'm using p for prime. Right, so statements 1 through 3, in fact, will hold, right? Okay, so here we showed that 1 through 3 do not hold in general. And we also observed here that 1 through 3 really, in the end, boil down to a product of this form, right? Something times something being equal to 0. Okay? So here we're saying that if we have a unit, then we can cancel, right? So if I have a unit, and that unit is part of a product that is equal to 0, then the other factor has to be equal to 0. Okay. So 1 through 3 would hold in that setting. Okay, so the integers mod 3, 5, 7, 11, and so on. The only solutions of this equation would be 0 and 1. This product being 0 would imply that either A or B is equal to 0, at least one of them. I can cancel. A, B equal to B, AC would imply there that B is equal to C. Okay, so in the integers mod P, arithmetic works in the usual way. And that's just because here, Y, as we've already observed, every non-zero element is a unit, right? So remember, when we're talking about a prime modulus, the units are everything other than 0. So in the integers mod a prime, arithmetic works in the usual way. Okay. Are you with me here? Any questions about what I'm saying here? All right. So then the integers mod p, where p is prime, are then an example of another sort of algebraic structure, and I think I mentioned this at the end of class last time. Okay, and that is a field. So a field is basically an algebraic structure in which you can do arithmetic as you're used to doing it, the rational numbers or the real numbers or any sort of familiar setting. All right, so a field it's a commutative ring, so multiplication is commutative. Okay, so a commutative ring with a 1. In which every non-zero element is a unit, so has a multiplicative inverse. All right, so some examples then, as we've just mentioned, so finite examples would be integers mod p, where p is prime. But then more familiar examples in the sense that they've come up in other classes, and maybe the integers mod p or mod n have as well, but certainly, for example, in calculus and a lot of the other courses that you take. So one might mention the rationals and real analysis. You certainly will talk about the rational numbers there. Real numbers, of course, right? Every number other than 0 has a multiplicative inverse. We can divide by everything other than 0. Similarly in the rationals, right, take a non-zero fraction, you just flip it over, take its reciprocal, that's the inverse, right? So every non-zero element has an inverse. And complex numbers turn out to be a field as well with the operations that we talked about last time. Okay, so if you've taken complex analysis, then you've encountered that probably in that course as well. Okay. So these are some examples then of fields. All right, and again, the point here in a field basically is in a field you can do or think about arithmetic. I'll just say here, as expected, right? So you have here plus, so addition, subtraction, multiplication, division, and it all works as you're used to it working. Okay, so familiar properties hold, and in particular you can divide by everything other than zero. Everything other than zero has a multiplicative inverse. Okay. All right. So what I wanted to talk about here is one last example for today, then ties in with a second question that's on the homework that I posted on Monday. Okay, and so it has to do with an additional example of a field beyond what's listed here. All right, so if we move away from primes, we're no longer talking about fields, right? So in other words, if I take the integers mod 9, okay, then this is not a field. Why? Well, because not every non-zero element is a unit. For example, 3 is not a unit mod 9, right? It's excluded from the list. Remember, what are the units? They're those numbers that are relatively prime to the modulus. So mod 9 would be 1, 2, 4, 5, 7, and 8. 3 and 6 would be excluded, right? Okay, so one might wonder then, well, okay, the integers mod 9 doesn't work. Well, is there something else that might? So in other words, is there a field with 9 elements? So a commutative ring with a 1 in which every non-zero element has an inverse. In other words, a setting again in which you can do arithmetic as expected. Okay, and so the answer to this question is yes. And in fact, I'll just say that in general, in terms of fields that have a finite number of elements, you can always do this, and you can do this only when the number of elements is a power of a prime. All right, so notice that 9 is a power of the prime 3, it's 3 squared. Okay. All right, so the example here is what's denoted on the handout with this notation. Okay, and basically what we're going to do is take the Gaussian integers that we wrote down last time, and we're just going to switch the arithmetic now to be mod 3. Okay, so in other words, we will multiply and add using the same rules, but now the addition and multiplication will be mod 3, and then we're adding in this I, which we're thinking of as a square root of -1. All right, so here, just in terms of a set of things, we're thinking about now numbers of the form a plus bi, where a and b are elements of the integers mod 3. Okay. And so I'll just say here that in the integers mod 3, if you think about squares, what can we get? So 0 squared is of course 0. 1 squared is 1. So is 2, right? 2 squared is 4, but 4 mod 3 is equal to 1. So if we think about the equation now, the same equation that we think about over the real numbers, namely x squared plus 1 is equal to 0. This equation does not have a real number solution, right? So in a sense here and this isn't exactly what we're doing, right? Because in the end it has to all work out. But we're basically making up a solution and throwing it into the mix, right? We're saying I is a square root of -1, it satisfies this equation, and then we get the complex numbers from this, right? And so basically here, this equation has no solution in this set, in this field, in fact, 3 is prime, right? And so we're just now introducing a solution to this equation, and then we're adding it, okay? So what we're doing here is now, just as in the complex numbers, we're thinking about this I. All right, so here, we're supposing here that I satisfies I squared is equal to -1. So this is not an element of the integers mod 3. It's something that we're adding in, having this property, okay, that its square is equal to -1. And then we're forming these new numbers built on the integers mod 3. Okay, so this is a set then of 9 things, right? I have 3 choices for A and I have 3 choices for B. All right, you with me here? So again, just like with the real numbers, then going to the complex numbers, here we're starting with the integers mod 3. We're supposing we have this new thing now that satisfies this equation that's not satisfiable in the integers mod 3. And then we're forming these combinations here, A plus BI, just like we get complex numbers from real numbers. Okay. So it's a set now of these 9 things. All right, so as a set then, what do we have? Well, B can be equal to 0, in which case we get 0, 1, and 2. B can be equal to 1, in which case we would get I, 1 plus I, and 2 plus I. And then B could be equal to 2, in which case we get 2I, 1 plus 2I, 2 plus 2I. All right, so these are the 9 elements of this set. And then the addition and multiplication are exactly as they were for the complex numbers. All right, so in other words, here, say, A plus BI plus C plus DI. Here, the sum is defined by, just say, adding real parts and imaginary parts. Okay. So A plus C plus B plus DI. Okay, so that's the sum. And then the multiplication here now, A plus BI times C plus DI, as given by the same rule. So we take for the real part AC minus BD, and then for the imaginary part AD plus BC. So basically think here about FOIL. Okay, but it's just now here, the only difference is that this arithmetic is mod 3. Okay, that's the only difference now. We reduce everything mod 3. Okay. All right. So just as a quick example here, so if I take, for example, these two numbers in this set and I multiply them together, then we're just doing the usual arithmetic but reducing everything mod 3, right? So we would have 1 times 2 or 2, and then minus 2 times 2 or 4, and then here, the imaginary part, 1 times 2 plus 2 times 2. but again, everything is reduced mod 3, right? So here we have 2 minus 4, which is negative 2, but mod 3, negative 2 is 1, right? So here, we would get 1 in this spot, and then we would have here 2 plus 4 is 6, right? And 6 is 0 mod 3, okay? Are you with me here? So again, the rules for addition and multiplication are what we wrote down last time for complex numbers. So it's just the same thing, now we're just reducing everything mod 3. Okay, and in this particular case here, notice what happened, we got 1. Okay, and so the claim here is that this is in fact a field. So here, this is a field. It's a commutative ring. Multiplication here is commutative. Why? Because it's all happening in the integers mod 3, and multiplication there is commutative, right? So since this is built on mod 3 operations, arithmetic mod 3, the multiplication here is commutative. Right, you with me there? In other words, if I change the order of the factors over here on the left, that just means that on the right, I'm simply in each of these products switching the order of the factors, right? But I can do that here because multiplication in the integers mod 3 is commutative, so there's no problem with doing that. Okay, because arithmetic mod 3 is. The unity here is, and again, you can see it through these rules here, just 1. Okay, so the integer here, mod 3, 1, that plays the role of the unity here. And then the last question, and that's really the key one here, is that of units. So remember, to be a field, all of the non-zero elements. Okay, so in this case here, each of these 8 things has to be a unit, has to have a multiplicative inverse. Now, here, we've already shown that, for example, these 2 elements are units, right? So we have inverses here. We've multiplied them together in order to get 1. Okay, so the inverse of 2 plus 2i is 1 plus 2i. Inverse of 1 plus 2i is 2 plus 2i. Okay, so those are the inverses here. And then similarly, for the remaining, we can pair those up and see that we can multiply to 1. Now, I'm out of time here. Okay, so what I'm planning to do is, on Friday, I'm going to make that something of an optional, so just like I was doing before the other exams, because your exam is right for the beginning of the week. I'm going to come back to this example and make a couple other comments about it, all right? Just a way of thinking about showing that all of the non-zero elements are units. But otherwise, I'm going to leave time for questions that you have, especially as relate to recent material or the homework that I assigned, so that there's time for us to look at those before the exam on Tuesday, okay? So again, on Friday, I'm going to come back to this and talk a little bit more about this example, and then otherwise, I will just leave time for questions on Friday to finish, okay? All right, so that'll be the plans that finish up the